Welcome everyone to our Data Science Fridays. Today we have Laura Tipton presenting a workshop on data biases. This should be super and all of us, right? We'll walk away feeling really positive, or maybe not. Anyway, Laura is an assistant professor at Chaminade University and has been working with us here in the Data Science Institute really since we got started. So it's been great having her as part of the team and really looking forward to your presentation, Laura. Should be fun.
Okay. I wanted to start with a caveat that while I started designing this workshop thinking about data biases and how to find and correct them, it really expanded from there, because otherwise it was going to be like a 10-minute lecture and like a, hey, let's play with R, and that wasn't the route that I wanted to go. So I'm going to let the word bias cover a lot of different things today, and we'll talk through each one so that we are quite clear on what I mean when I'm talking about biases in each iteration, right? And first, I'd like to take a minute to reintroduce myself. I am Dr. Laura Tipton. I am a white woman. I'm of non-Hispanic origin. I'm in my 30s. I'm a feminist, an LGBTQAI+ ally. I grew up in Virginia. I have a background in statistics and computational biology. I've been married for over a decade, and we have a 3-year-old who is usually in daycare, and she is shown there on the bottom right of the screen. We've lived in Hawaii for about 5.5 years, and I currently have a small group of students who do research with me on microbiomes at Chaminade University. And Chaminade University of Honolulu is located in the Moku of Honolulu, in the Apua of Waikiki, and in the Ili'i of Kaimuki. And this is land that was tended for generations by Indigenous Hawaiians whose knowledge systems shaped Hawaii in sustainable ways. And that then goes on to influence me and my work. So why did I just give you the bullet point life story of myself? Because these are my personal biases. These are the things that shape my worldview and therefore are going to shape the algorithms and the processes that I design, right? So this really falls under the category of personal biases. And then today we're also going to talk about data biases and algorithmic biases. Right, so technically, I am very into definitions of things, and this came out of transitioning fields from medical science to environmental science and biology, well, all within biology, right? But it really gave me this love of figuring out what the exact definition of words are. And so psychology today defines a bias as a tendency, inclination, or prejudice towards or against something or someone. Therefore, it's not inherently good or bad. And before you're like scratching your head and being like, what on earth is she talking about with a good bias? Let me show you. Which of these would you rather hug? Right? That's a bias. That's a good bias. That's the kind of bias that has kept humans safe over many millennia, right? You know, big sharp teeth, scary, run away, soft and snuggly. Okay, let's hug that, right? That's a good bias. It's not all that common. It's not common that in this this type of work that we get to talk about good fuzzy things. So I did want to start with that. Generally, for our purposes, we will more commonly be using the Brookings Institute definitions of biases, and in particular algorithmic biases. And they're defined broadly as it relates to outcomes which are systematically less favorable to individuals within a particular group, and where there's no relevant difference between the groups that justifies these harms. Similarly, a couple of data scientists writing for Medium agreed that data scientists should be aware of the possible biases involved in the design, implementation, and use of analytical systems. And so these are things that I have links to that you can look into more if you want to look into more of the definitions of data and algorithmic biases. And the reason that we're doing this is that because some of the common implication of biases, and particularly negative biases, is that it amplifies historical and cultural biases. And I think it's safe to say that humans in general over history have kind of sucked. we're getting better. I hope. I like to think we're getting better and less biased and more equal, more headed towards equality. But you know, our data and our history have kind of sucked. You can also learn incorrect patterns or attributes if your data is biased, and then you can ultimately cause unjustified harm to one group compared to another, or create uneven access to benefits. And I hope it's a safe assumption to say that these are things that we'd like to avoid. So let's talk a little bit about personal biases. I already told you many of mine, but this really stems from qualitative research. And this is a style of research that we don't talk about in computer science and data science all that often, but it's data from firsthand observations, interviews, open-ended questionnaires, focus groups, participant observations, recordings, documents, artifacts, all of these squishy things that we don't like to think about when we think about data, but they are data. And it's very common in ethnography and psychology, and has been increasingly common in mixed method analyses that are really becoming more and more common in data science. And so in qualitative research and in mixed methods analyses, the data are interpreted, and they're interpreted through lenses or theoretical perspectives. And maybe you've heard of some of these things, like feminist perspectives, queer theory, disability inquiry. All of these are how you frame and find themes within that squishy qualitative data. And so generally they start with a statement of biases. And John Cresswell writes that you want to clarify the biases that the researchers brings to the study. And this self-reflection creates an open and honest narrative that will resonate well with readers. Reflectivity is a core characteristic of qualitative research, and good qualitative research contains comments by the researchers about how their interpretation of the findings is shaped by their own background, such as their gender, culture, history, and socioeconomic origin. And so the idea is that the researchers' biases plus this interpretive lens will increase reproducibility. And in fact, that someone with different biases would not be able to reproduce the original researchers' findings, even if they use the same interpretive lens. And so if we flip that into, into developing algorithms and doing data science in general, developers' biases can really impact what they deem as acceptable. And if we think about things like Facebook, and now I'm old enough to remember when Facebook first came out, and you put in your classes because it was limited to college students, and then you could contact anyone within your classes. And now, we know Mark Zuckerberg was the key designer of Facebook, or one of the key designers, depending on who you ask. But had a woman designed Facebook, I don't think it would have been so easy to contact anyone in your classes, because that's an open invitation for harassment, and women know that. And Mr. Zuckerberg probably didn't. Similarly, do you really want me designing a replacement for Grindr, given my life experience? Probably not. But we don't know who's designing our dating apps, right? And maybe we should, because whoever's developing them is going to put their own personal biases into that algorithm. Okay. And so now I'd like to take 5 minutes and have you consider your own personal biases and how they may impact your data analysis and your algorithm development. So I'm going to pause for about 5 minutes and let you start writing this down. This is the interactive component that requires either pen and paper or a word processor. No, Katie, you don't need to worry about sharing it. In fact, I'm not going to ask you to share it at all. This is really for you and your own self-reflection. I'm not asking anybody to out themselves about anything. Okay, we're going to come back together and start talking about data biases. But before we do, I just want to note that your personal biases may change over time, and that's okay. There's nothing wrong with that. But I think going forward that this is something that we should really borrow from from qualitative research and apply it to our quantitative research. I think it would probably help make things a little bit more clear, a little bit more often. Okay, so moving on to data biases. So some of the common causes of data biases are uneven training data, historical biases, closely related to cultural biases, correlated variables, and data that doesn't capture the actual value of interest. And we're actually going to walk through these one at a time, and sometimes it'll be examples of where this has gone horribly wrong. So starting with uneven training data, the most glaring example of this that I've ever heard of comes from protein-protein interactions, where less than 1% of protein pairs are predicted to interact. So if you're trying to predict whether or not a pair of proteins will interact, you're looking at a database that has 715 million non-interacting pairs and only 77,000 interacting pairs. So if you're trying to create an algorithm that can predict whether or not proteins interact based purely on the data that's in these databases, you have highly uneven training data or uneven classes within your data. So what can you do? You can make a table, and hopefully it looks something like this one, where you have 34,000 versus 28,000, and yes and no. But if you have something more like the protein-protein interaction databases, what you want to do is, as you're building your algorithm, you want to confirm that all of the classes are present in both your training and testing data. And that can be a little bit difficult. So that can involve potentially up or down sampling your training data. And if these are words that sound like a foreign language to you, that's fine. These are things that you can certainly go and look more into, but they are actually relatively straightforward statistical techniques, and so they're fairly well established techniques that can be done. What gets squishier or less well established, I love the word squishy, I'm sorry guys, it's one of my favorite things, and it is in no way meant as an insult. So when I talk about squishy sciences, it's because I adore it, right? Not because I think they're less than hard sciences. Right, so historical biases, right? These are things that have been in our history, and our data tends to come from our history. And so I thought this cartoon really captured it very well about machine learning algorithms and making the robot apocalypse short-lived, because as the character on the right says, if you look at historical data, the vast majority of battle winners used pre-modern weaponry. And so similarly, a predictor or a description of the future US presidents would be an older white-haired white male named James, because 6 of the 45 presidents have been named James. And obviously that's a small sample size and an extreme example, but you wouldn't necessarily expect that they would be named James. And so closely related to historical biases are cultural biases, and these are just things that you kind of have to be aware of. And one of the most glaring examples in real life is women have actually only been legally allowed to own their own bank account since the 1960s, and that's only been enforced since about 1974. And that's not that long ago if you're looking at banking records. That's literally my grandmother, when my grandfather died, didn't have her own bank account. And in fact, 75 countries still restrict women's right to manage their own assets. And so, this is something to keep in mind if you're looking at historical banking records in the US and trying to predict whether or not someone will default, then you only have so much data that actually includes women. And similarly, if you start looking globally, you have to know culturally whether or not women are allowed to manage their own bank account, whether or not they have access to IDs in order to get their own bank accounts. All of these kinds of issues come into play. And so this is where you have to know your data, and you have to know the historical and cultural biases that go into it, so that you can hopefully avoid amplifying them, assuming that's your goal. Correlated variables are also very common, and this is an actual statistical problem. And so highly correlated variables will provide the same information to your algorithm, and they violate the assumption of most models. And the way to check for them is to create a diagram kind of like this. This is called a core plot. And what this does, this one in particular, it shows strong correlation between coral coverage, temperature, and salinity in Kaneohe Bay. So if we're interested in predicting something else about this data, those temperature and salinity in particular are really going to give us the same information. They're not going to provide any new information, and it's going to violate a statistical assumption if we start including that. And that brings us to one of the most famous biased algorithms. And so this is the COMPAS algorithm. And so in 2016, ProPublica broke a story about the COMPAS algorithm, which was used to predict recidivism rates in the US, and therefore bail rates and probation and all sorts of things associated with that. And while they didn't ask for race explicitly, for variables that are highly correlated with race, meaning family history arrest and zip codes, which are incredibly tied to race due to redlining. And so they ended up amplifying these historical biases where in the past and even currently, judges will give stricter sentences to Black criminals. And what ProPublica found was that African Americans were assigned higher risk scores than whites, even when they had the same estimated probability of reoffending. And if you're interested, there's a whole article there about it. And that actually brings me to data that doesn't capture the value of interest. And the number one variable where this is an issue is actually race. Because when we say race, we're often looking at racism, right? Race has no genetic underpinnings. It's a social construct that was really created to control access to power and resources. And for example, on the slide, when we talk about Asian Americans, we actually mean a whole slew of different populations. Similarly, Pacific Islanders, here we've seen that Pacific Islanders really encompasses a lot of different populations. And the pandemic really shed light on the necessity of breaking things down, and particularly beyond AAPI or Asian American Pacific Islander that we see on mainland algorithms and mainland data collection. So when people talk about race, even when they're talking in scientific studies, most likely what they should be talking about is racism and how it affects these different groups and what they're, how they're treated structurally in environments, or what they're being exposed to, or what experiences they have on a daily basis and how that is impacting them. And we just kind of summarize it in this catch-all term of race that isn't actually what we're interested in. And on that fun note, we're going to move on to algorithmic biases. So if we want to, by the time we've looked at our data and developed an algorithm, we still need to measure biases. And IBM in particular has compiled 70+ fairness metrics to compare classes. And these measure but don't mitigate bias. And these metrics include things like equal opportunity difference and average odds error, which it computes the average absolute values of the difference in true positive rates and false positive rates. And also things like Euclidean distance between the predictions for the two groups. So these range from fairly simple to fairly complex. And so what can we do if we measure the fairness or measure the bias in our algorithm, what can we do to try to fix it? Well, number one, we can remove positive reinforcement loops or negative reinforcement loops, depending on your lens and how you're looking at it. You can add human in the loop decision making, or you can look at ensemble methods, and we'll walk through each one of these fairly quickly. Okay, so number one example that I could find of positive reinforcement loops, and you can see that I've been working with criminal justice majors lately, perhaps, because this one is PredPool, which is predictive policing. And in fact, precincts aren't required to disclose whether or not they're using PredPool or any other predictive policing. But what this particular algorithm does is it sends officers to neighborhoods to check for drug use based on where previous arrests were made for drug use. So what this led to is increased drug arrests in neighborhoods that had previous drug arrests, and decrease arrests in safe neighborhoods. And hopefully you can see where this is just feeding back onto itself, because it predicts, okay, we're going to send an officer over to this area to check for drugs. Oh, look, we found drugs. Let's send an officer back to that area to check for drugs. And it just creates this reinforcement loop. Technically, it's a positive reinforcement loop, but the outcome is obviously quite negative. And so, it's going to require some other kind of input to break that loop. And in fact, lawsuits have been ongoing against Predpool and the precincts that use them since 2019, at least. So one of these ways is to add a human in the loop. And the most simple human in the loop is to add a reject option classification where the human can override the algorithm. Again, that's kind of the most simple. And in fact, Dr. Travis Mandel of Hilo, who is also a part of the Hawaii Data Science Institute, he has done a lot of work on human in the loop AI. And so if you're interested in that solution, I strongly encourage you to go look at his work. And finally, we come to ensemble methods. And this is just combining several algorithms together to outperform any individual algorithm. So the little figure, you have to use both, or rather all of A, B, and C lines in order to actually separate your pluses and your minuses. And so this is a broad solution and can actually include adversarial classifiers. And those are classifiers that will purposely generate false data in order to, that looks like it could be real in order to try to trick your algorithm and trip it up. So then we have some general and legal solutions. And so these include requiring explainability, and explainable AI is definitely on the rise. And so this comes into play in things like the Equal Credit Opportunities Act from the 1970s. And this requires justification for rejection of a loan application so that the loan officer can't just be like, oh, computer said no, so no, right? So requiring laws like this is certainly one legal solution to AI biases. Making sure that you include protected groups in your AI development. And in fact, there's an Indigenous protocol and AI working group that have been working on how to do this and how to do this well. You can use external review panels. And I'd posit that you can contact Hawaii Data Science Institute about this, and we will work to put one together for you. You can create safe harbors for sensitive information, and these include things like disconnected servers. And I know that UH has several of these types of things that have no access to the internet, and therefore create a safe space or a sandbox in which to play with your algorithm before it's deployed. We can push for an FDA equivalent for algorithms that generally provides federal oversight over algorithms that are deployed on the public, and essentially creates a federal level of an external review panel. And we can write an algorithmic impact statement. So an algorithmic impact statement, and this is something that we're going to do, right? So this really addresses who is responsible if other people are harmed. How much of the algorithm is explainable? What sources of errors or biases are there in the data? What's being done to correct those sources or those errors? What groups may be advantaged or disadvantaged by your algorithm? And what harm may come to any disadvantaged groups? So with those in mind, and particularly with the last two questions, like what group could be advantaged or disadvantaged and what harm may come, I'm going to ask you to start writing an algorithmic impact statement for yourself. And so this is, if you're already developing an algorithm or a product, you can use that. And since I know that many of you are not actively doing that, if you don't have one that you're developing, consider a hypothetical automatic college acceptance algorithm. So where would you get the data? How is it biased? How can you fix those biases? And who could potentially be harmed by such an algorithm? So we'll give you 10 to 15 minutes, and then we'll break into some small groups to talk it over. Okay, I'm going to ask you to go ahead and pause here, and I'm going to open some breakout rooms with 2 to 3 individuals in each breakout room. And that way you can start bouncing ideas off of each other and make sure that you get a different personal biases perspective on what you're working on. I'm just going to assign them randomly, so please go ahead and enter the one that pops up. And we'll let you guys share for 10 minutes or so again, and then we'll come back together to close out. All right, welcome back. Does anybody want to share what came out of their discussions or what came out of their initial thoughts on an algorithmic impact statement?
So we all kind of discussed about the college admission one, and also it was easy for us to kind of communicate about that. But our general consensus was that we didn't want to write this algorithm, just because like we were talking about the institutional, like racial institutional biases of the SAT test, which is, seen as kind of like the benchmark for college admissions in the first place. So if one metric is flawed, then how are the rest? How do we deal with a flawed system in the first place? Yeah, and then we talked a bunch about like even the college admission essays, which from personal experience, a couple of my high school friends or acquaintances, let's say, had paid for essays to be written for them or to be. Yeah, I'm also from South Korea. I went to school in South Korea, and which is much more prevalent there. I know a couple of students that I was in high school during the scandal of the Korean SAT test being released to the public, the answer test, and so for 6 months, I think the SATs were banned in Korea. So people had to fly to other places, or they got screwed for that year. But we were also talking about how the admissions essays. Well, I mentioned that the admission essays was kind of hard to quantify, also because machine learning would have to be implemented, and also someone's voice might not be able to be carried on, etc. But basically we just did not think it was a good idea in the end, basically.
I think that's a really perfect example of why an algorithmic impact statement should be written really before development starts, as a way of thinking through the process and thinking through what could possibly go wrong and how people could be harmed and impacted by your algorithm. And you're absolutely right. You used some of my favorite examples that I use with my undergrads about, the SATs are super racist and biased, and that they are in fact more, more an indicator of socioeconomic status than of anything else. Similarly with the GREs. So that was really great. Would anybody else like to share? Okay, that's okay. That was a really great summary. So we can go ahead and move on. Right. So I wanted to close out on kind of what can you do. I realized that like this can be a super depressing topic where we're talking about racial inequalities, sexism, all of these things, and so I want to end on what can you actually do, what like concrete steps that you can take. Right. So you can recognize and acknowledge your own personal biases and write an algorithmic impact statement. And you'll notice that those top two things, that's exactly what we've done today. Right. You can check your data for obvious biases. These are some of the things that I talked about in the data bias section. Or you can use an external review board to check your algorithm output for unintended biases. And like I said, feel free to reach out to the Hawaii Data Science Institute to help you set that up. I'm volunteering us for that, Gwen. And you can advocate for a federal oversight of algorithms that are used on the public, such as the predictive policing and the COMPAS algorithms and facial recognition and that kind of thing. I've created a slide of some more resources, and this is just a handpick of some of the resources. But I did want to highlight that we've actually, the Hawaii Data Science Institute has actually hosted a couple of talks on these topics, including removing unfair bias in machine learning by Trisha Nakayama, and tangible steps towards AI or towards algorithmic accountability. And I forget that speaker's name, but those are two really fantastic women who came and talked to us about these issues and what can be done. And in fact, Trisha Nakayama talked about IBM's AI Fairness 360, which is the last link on this list. There are many, many more resources. And I don't think I could actually talk about algorithmic biases without mentioning the movie Coded Bias. And this film is available on Netflix. And if you haven't seen it already, I cannot recommend it strongly enough. I think that this is a topic that you're interested in. And it starts with facial recognition software and goes all the way through citizen surveillance and also the social currency that is used in China. It covers all of these things. And so, you know, I really toyed with the idea of just having you guys watch this for an hour and a half instead of listening to me talk and writing your own algorithmic biases. So, you know, I cannot recommend it strongly enough. That's it. That's actually my last slide. So if you guys have any questions or concerns in general, and then after that, I am going to ask the HITSE fellows to stay on for just a couple of minutes to discuss the next couple of weeks. But questions?
Hey, I have a question, Laura.
Uh-huh.
I really like that slide you had on what can you do, because it's sort of the mantra, right, that you want to try and encourage scientists to follow. Did you sort of come to that as a synthesis of everything you've digested, or is there a citation that says this is a good set of rules to follow that we can cite in, say, for example, the work that we're writing or the proposals that we're writing, things like that?
So it's a combination of my synthesis and the Brookings Institute reports.
Okay.
They're the ones that really emphasize algorithmic impact statements and external review boards were their two big findings. And then ultimately it's my opinion about recognizing your personal biases.
Okay.
Federal oversight for algorithms comes from the Algorithmic Justice League, and that's cited in Coded Bias among many other places. So yeah, a little bit of both. But if you need a citation, I really recommend the Brookings Institute report.
Okay, great, thank you.
So I don't mean to have, oh, sorry.
Yes.
I don't mean to have like a bleak question after such a great presentation, but how about what if we have a problem that is inherently biased? Like, even though we have all these what can you do's, if the problem that we are looking into has inherent, like we can't get rid of this bias, then what should we do then? I guess this is also like, you know, the whole AI self-driving car thing, the trolley problem, I guess, which is I think common in self-driving cars. Yeah,
that's a really good question. I don't know if I'm qualified to answer it. I think it's really going to depend on the developers or the people that are involved, and bringing in the stakeholders and getting their opinion and trying to make it as unbiased as possible, or as fair as possible, however you define that fairness. And you know, that has to do with equity and equality and equal access and all of those really social equity terms. You know, is the goal equal access, or is the goal to give everybody the same thing? And then it, you know, it really depends on both what you're trying to do and the opinion of the stakeholders and how that might change over time. Does that kind of?
Yeah, it was also kind of like, I think, a hard question in general. And I agree with the equality and equity, the difference between that, which one is more fair, right? Just want to say thank you so much for the presentation. I had a great time today.
Oh, well, thank you. I'm sorry, it's a little depressing.
Hey, Laura, can I ask a question?
Sure.
Okay, so I guess like my initial interpretation of like identifying biases was a lot of this kind of starts with analysis of qualitative traits and then outcomes to identify the biases, and then you kind of use those to look at the you know, quantitative research and algorithms that are being developed. So like, I guess, is retrospective the right word for implementing, you know, correcting for biases retrospectively? Is there a prospective way to basically look for things that you would never have even thought of?
Oh, that's tricky. So I think that's where these algorithmic impact statements before you develop an algorithm can come in. And again, getting stakeholder buy-in and external reviews so that somebody else comes in and somebody from your potentially disadvantaged, if you can, bring in somebody from the potentially disadvantaged group, or multiple people ideally, because no one person speaks for their entire group. But yeah, I think it's about bringing more people to the table, and before you start, right? I think that can be important, or to the extent possible, to bring them in early and often. But I don't know that there is a tried and true, like, this is what you should do before you start, to prevent it or anything else.
Laura, I was wondering when we might see something like the equivalent of an IRB board review if you have an algorithm in your grant proposal, or similar to the animal use agreements and things like that. I think I'm wondering when that might happen.
I'm hopeful that kind of thing happens, although my university doesn't even have an IACUC, so it always kind of surprises me. I guess we don't actually do animal research, but it still seems surprisingly oversight to me. So I'm going to rely on you and Hidsi to create this, right?
Yeah, we were just, because we have to, one of the things I've been kind of advocating for is, if your grant requires, some kinds of resources, storage resources, computing resources, there's no checkbox right now in our review cycle, within our migrant system to indicate that. But if you have animals or human research or anything like that, then there's all those. But so we're just wondering, where's the checkbox for where's the cyber infrastructure checkbox?
Is there a checkbox for the data management plan?
Yeah, not on my grant. That's
okay. Because that should address some of that. It doesn't really get into all of it, but some of that ought to be included in the data management plan.
Yeah.
We could push for that too. Let's advocate for that as well.
Yeah, I'm just curious about, maybe Jason knows. I don't think Peter is on, but I wonder if this gets discussed in the review panels for these various proposals, these, algorithmic AI proposals. Do they talk about this in the review panels? Jason, have you been on one? I have not.
I have not been on one that's touched on this topic, because this is all very, very new. And even for the FAIR stuff,
right?
It was only like maybe a year ago that Dan Katz started talking about FAIR in cyber infrastructure as a new topic area that cyber infrastructure folks haven't wrapped their minds around yet.
Yeah, interesting. Yeah, I was wondering about that because there's all those, how many of those new AI institutes are there? That there's like 4 or 5. That's a lot.
Yeah.
And you wonder, is this part of their core value statement? Right? We can hope, right, Laura? Put on your optimistic hat. Put on that optimistic hat.
My optimistic hat is that, our data science students don't leave without taking 2 ethics courses.
Yeah, awesome. That's
so, and so I've been trying to, bring some of that over to the fellows. But I definitely think no data scientist or computer scientist should graduate without taking an ethics course. But again, those are my personal biases, right? They're highly influenced by working at a small liberal arts college. So
yeah, that's cool though. Yeah, this is really interesting. Thank you, Laura. This was I learned a lot today. It was good. All right, do we have anything else today? It is Friday. Head out to the beach, right? Jason, are you there now? Have you got your surfboard ready to go?
No, I'm at the lab today.
Okay.
Yeah.
Well, it is Friday. Happy Aloha Friday and Pauhana time, right?
yeah.
Almost. Except work more till 5 o'clock and then go back to work, graduate students, back to work.
I just need to borrow the data science fellows for 2 minutes.
Yeah, you take
Everyone else is
care.
free to leave. Thank you so much for coming and showing
you,
me that this is not a total waste of my time to
No,
be
no,
concerned
awesome.
about this.
Oh, super good. Okay, take care. Bye. Have a great weekend.